This is lecture 12 of our course EEE 4705 microcontroller based system design. In this lecture, we will try to learn how to interface LCD and keyboard with 8051 microcontroller. So this particular lecture is intended both for theory and lab portion of the course, because in your lab in experiment 3 and 4, we basically try to learn these two things: to interface LCD and keyboard with 8051. And also this lecture will be very helpful for your project as well as complex engineering problem. So let us start. First of all, we will start with LCD interfacing. So the LCD device or display we are going to use for this lecture is this one actually. The model number is LM016L and it has 14 pins. In general, you will see different versions of LCD like the ones we have nowadays. Some of them has 16 pins as well, but in general the overall work procedure, how we actually interface those are almost similar. So our lecture will be focused on this particular version of the device, and it has 14 pins. So briefly, initially we will try to describe what are the functionalities of each of the pins we have here. So if we start from here, so we have VCC and VSS. So VCC is sometimes also called VDD, which is the power supply basically. So we have to give 5-volt power supply to power it up, to turn it on, and VSS is ground, right? Then VEE is to control the contrast of the display. What we do, we generally try to give variable voltages to control the contrast of this display. So with the increase or decrease of voltage, contrast also changes. So what we generally do, we just try to use a potentiometer, connect that with 5-volt, and try to give variable voltages through this pin in VEE that controls the contrast of our display. Then next one, RS or register select. To understand this, what you have to first of all understand is we have two different very important registers inside of this LCD display. One of them is called command register. The short form is command register, and another one is data register. Whenever we use this device, there are different kind of behavior which we can control, like the cursor type, then what kind of font it will show. There are different kind of behaviors that we can control. So to control those, we have to send some commands, and those are stored in command register inside of our LCD. And another one is data register. So whenever we try to display some characters, we send them through different pins, which we will discuss later on. But basically we send them, and somehow they have to be stored inside of our LCD in some memory location, so that it can store that and then display that onto the device, right, onto the display. So that is done through the help of data register. So whenever we send any kind of data, character data that has to be displayed on the display, that is first of all stored in data register. So what we generally do for this particular pin RS or register select, we basically select in which register we want to save the data. Okay, so these 8 pins D7 to D0, these are basically the data bus for this particular LCD display. So whenever we send any kind of data or receives any kind of data, that is done through these 8 pins, right? So whenever we send some data to our LCD display, so that will be either saved on command register or data register based on the RS pin. So if we send 0 to RS, command register will be selected, and whatever we send, that will be sent to or stored into our command register, and if RS is equal to 1, that will be stored on data register, and that will be displayed onto the display. So this is how it works. So another thing is also, we just talked about sending the data to our LCD. Sometimes it will happen that we want to read some data from our LCD. that is also possible. So for that case, we have this read write RW pin. So if read write pin is 0, logic 0, that means we want to write some data onto the display, right? Or any of the registers, on any of the registers, data register or command register. And whenever read write pin is equal to 1, that means we want to receive some data either from the command register or data register, right? So we will see. Now we are just talking about every pin description briefly, but later on we will detail on each of the pins, how we can use this device in different modes, how we can send different data, get different data based on different situations. So we will discuss those, but briefly now we are just trying to understand what are the functionality, basic functionality of each of the pins. Okay, then enable. So whatever you do in this RS pin and RW, or even in these pins, I mean in these 8 pins we have to send data or receive data. Whatever you do to actually make that happen, finally you have to use this enable pin here. Okay, so what we do, this is not similar type of pins like RS or RW. It doesn't work on just 1 or 0, so you have to give a negative edge triggered signal or positive edge triggered signal. So that means either high to low or low to high signals, just like your clock pulses. So if you give that, then whatever data that is available in RS, RW, and also in this 8 pins data bus, based on those commands, similar activity will happen inside of the display, either to receive or send data, right? So what we do whenever we want to write some data, the signal in enable pin should be negative edge triggered. So that means high to low signal should be given. So first of all, there should be high signal, then some delay, then there should be a low signal. So in this way it works. So we will discuss why that delay is needed between high to low pulse, but this is how enable pin works. And we have already talked about these 8 pins, D7 to D0. These are just data bus to send some data or receive some data. So that can be either command data, that can be character data, anything, any kind of data can be sent or received, and we will discuss that later on. But what you have to understand, whatever command or data you want to send or receive, you will give the corresponding bits to RS, RW, or in this 8 pins D0 to D7. But after you do that, to actually latch that information, you have to use enable pin. So that should be either high to low signal or low to high signal. Only after that the command you have given will be activated. Okay, now let us talk about the command codes. As we said earlier, command register stores the data to control the behavior of LCD. So these are called command codes. Command codes are stored inside of command register to control the behavior of LCD. Okay, so what are these? These are just 8-bit values. We send them and store them to command register, and to send this data we will talk about specific codes to control different behaviors. But first of all, how to send any of the data, let us try to understand. So what we do, we first of all make RS is equal to 0 to select the command register. Then read write pin should get 0 signal or logic 0 signal, because 0 means what? For read write, 0 means we want to write some data, and 1 means we want to read some data from the LCD, right? And then after that we send the corresponding 8-bit data for specific commands. Okay, these are done through this pin. So basically RS should be equal to 0 here, then RW is equal to 0, and whatever command you want to say, corresponding 8-bit value is sent to this pin. After that, what we do in this enable pin, we have to send a high to low pulse. Okay, so something like this: first high, then low. So negative edge trigger, because we know from the previous page, whenever we want to write something we have to send a high to low pulse. Based on that we are doing that, right? And now we are going to look at some of the commonly used command codes to properly initialize our LCD before we try to write any kind of character data onto the display. So let us look at that. So there are a lot of command codes to control different behaviors of LCD, but we will not talk about all of them because in most of the cases we will never need those. So the ones which are most common and useful, we will talk about those and try to look at how display behaves based on those commands. Okay, so some of them are called initialization codes, right? So we always use them before we try to write some data. So whenever we start the display, these commands are given most of the time because these are needed for initialization, properly initialize the device. So let us look at this particular types of code. So LCD mode selection, this is one of the initialization codes we have talked about. So whenever you want to initialize your LCD, you have to select what kind of fonts are being shown, because you will see each of the character can be shown in this kind of pixels. So this is intended for one character, and if you look closely you will see in the horizontal direction we have 5 pixel, in the vertical direction we have 8 pixel. So this is called 5x8 font. And if we use this command, which is 38, we will select this kind of display. Okay, this kind of LCD mode, which is we are going to stick to only one line, and each of the characters will have 5x8 font. So if you count them, you will see that we have 16 different characters that can be shown here. 1 2 3 4 up to, you can see this will be 16, and we can have 2 lines like that if we want, but here we have only selected one line and 5x8 font. And then let us look at the next one. For the next one, again we are selecting one line, but here the font type is 5x10. So you see here what we do, we just add some pixels here as well to show different type of fonts. That's it. Okay, so in most of the cases we will never need those, but sometimes it is helpful. But you see, because initially or in general how the display is built, we will have this kind of pixels. So that means all of the characters have 5 pixels in horizontal direction and 8 pixels in vertical direction, and like that we have 16 multiplied by 2, that means 32 blocks to show 32 different characters. This is for the case of 16x2 LCDs, but you can have different type of LCDs. But for this one, if we have this code 38H, that means we are going to use this mode. That means 2 lines will be activated, and for each of the lines the font will be of 5x8 pixels. Okay, in most of the cases we will try to use this particular mode. Now let us look at the next one. So here enable or disable display element. So it is also another one of those initialization codes. We have to always, most of the cases we will have to use those before we start writing anything onto our LCD display. So there are different possibilities we can choose from. So all of them have different command codes. So one of them is disable display cursor and blink. So if I show you all of them one by one, then you will understand what is cursor, what is blink, what is display. So this is for disable display cursor and blink, nothing is shown here. Then enable display, disable cursor and blink, still nothing is here. So here the display is enabled but nothing is written here, so that's why nothing is shown. Then enable display and cursor but disable blink. If you have that, then you will see there will be a cursor here, and whenever you write something, you will see that the cursor is also there. Okay, and another thing you can do, instead of the cursor you can have this kind of thing which is called blink. Okay, and you can turn both of them on, so there will be cursor, there will be blink. So we have to choose one from here to have one of the modes from all of these possibilities. And also for these three we can say the same thing, we have to choose one that will select the LCD mode. Then another command code, which also is one type of initialization codes. So this controls the cursor behavior, how it will behave whenever you write something. So there are possibilities like decrement cursor on read write, don't shift screen. So you see here, if you look at this particular one, whenever you choose this mode, if you write, the cursor will decrement each time you write something, but screen is not shifted. So what that means, if you look at the next one, you will understand. So for the next one, you will see both cursor and screen will shift each time you write something. So you see here, for this one, if you write something, actually the screen is also shifting. Because of that, the cursor shift you cannot see. Okay, so each time you're writing something, the display is moving to this direction, also the cursor is moving to that direction. That's why the cursor as it seems here is fixed. Okay, but this is what is happening here in this mode. And the third one is the one we're going to use in most of the cases, or in all of the cases, this one. So increment cursor on read write and don't shift screen. So you see, screen is not shifted, but if each time you are writing something, the cursor increments its position to the right. So this is the one we are going to use in most of the cases. Then the next one, in this case, the display will also shift. So you see, the cursor is moving to the right, and also display is moving to the left. As a result, as it seems here, is cursor is fixed and only the data is moving, or the characters are moving to the left. That is the one. So but in most of the cases, this is the one we are going to use. Then the next comments we have, these are some of the ones we have to use initially whenever we start our display, but sometimes in between writing characters we can use them also to control the position of cursors and different kind of things. So first one, clear display. So whenever you have written something, if you just give this command, it will clear everything and come here. Okay, and whenever you have written something, it will just clear everything and make the display blank. And the next command, return home. So if you have written something, after you have given this command, it will just return to the initial position here. It will not clear everything. So what we do, whenever we initially start our LCD screen, we actually give these two commands, so that if by any chance, for any garbage value, if there is something written in the display, that will be cleared up, and also we will return to the initial position from where we want to write. Okay, so next, a similar kind of display commands we have here. So if we want to move the cursor position to the left, we can use this command. You see, just cursor position is moving. So when we move that, if we write something, that particular character will be written or shown in that particular position of the cursor. Okay, so that's why this is needed. And also we can move cursor position to the right. So each time you are actually giving this command, it will move its position to the right by one block. Okay, so even though here you can see it's actually moving to the right one by one gradually, but this is happening because I'm giving this one for each command simultaneously, one by one, multiple times. As a result, it is moving to the right for multiple times. Okay, similar thing, you see, if you want to shift the display, enter display to the left, you can do that using this command. So each time you give 188 command, the display will move to the left by one block, and same goes for the next one. It will shift the display to the right by one block in this way each time you give this command. And the last two, these are, if you want to write something to a specific position, you can give their addresses. So each of the blocks we have, they have some particular address. So the first one here, if you want to write something, this is the address 80. Okay, so from here up to 8F, these are the 16 addresses we have. And here this starts from C0 and from here CF. Okay, so that means if you just give this command and then write something, so let's say if I say 80, 81, 82, 83, 84, so let's say I give command 84 first, then write a character. The next character that we have written will be shown here. In this way we can change the position where we want to write something. Okay, we will see that in the example code we will try to understand that. Now let us look at another thing which is quite important, checking the busy flag. So whenever we send any kind of data to LCD or do any kind of thing to our LCD, it takes some time to actualize that for its internal operations to execute that. So whenever it does, it cannot take any more commands. That's the idea. So we call that busy condition. So whenever our LCD is busy, it cannot take any more commands, so we have to wait for that and send the next command afterwards. So how we can actually get a signal for that our LCD is actually busy, we cannot send any data. So for that we have a busy flag which is actually given by our command registers. We have to read that from command register, and microcontroller will read that and understand currently our LCD is busy, we cannot send any command. So whenever it is not busy, we can send the command. So how we can actually get that signal? Whenever you have sent some signal, let's say, next what you want to do, you want to check whether our display is busy or not. So for that what we do, we make rs is equal to 0 because we want to read from command register. Okay, and here I think it should not be 0, it should be 1 because we want to read something from our display. That means our W pin should get 1. And then what we will do, we will try to send this command to our display to let it know we want to read something which is busy flag, right? So if we do that, if we want to do that, we have to finally give a low to high pulse to our enable pin which is for reading something, right? So if we do that, we will have to check here, specifically here in D7 pin, and command register will send its data or the busy flag through this particular pin. Okay, so we have to check that, and whenever D7 is equal to 1, we have to understand LCD is busy. We cannot write anything until it becomes ready to receive new information. And if we get D7 is equal to 0, that means it is not busy anymore. We can send new information, send new data, do new things with our LCD. So this is how busy flag is checked. But in general, in the first code, you will see we don't have that facility to use busy flag. Rather, what we will do, we will just give some delay after each command so that it has enough time to do internal operation for each commands or for each data. So we will just vaguely we will assume some amount of duration for that delay so that it can do, LCD can do its internal operation after each command and it is not busy anymore. So that will be done, and later on in the next example we will see how we can improve upon that by checking this busy flag so that we don't have to wait arbitrarily for giving the next command. Okay, after we have given necessary commands for the display to behave as we want it to behave, we can send data so that characters can be displayed onto our display, right? The characters we send is done using ASCII codes of that specific character. We know that for any character like 1, 2, 3, 4 or ABCD, whatever you have, for most common characters, we can actually show them or represent them using their 8-bit ASCII values. So that is what we are going to do. We are going to send them using this 8-bit bus and send that ASCII 8-bit value for that corresponding character which we want to show. And because we want to write something, these are the values we have to send to different pins. RS should be equal to 1 because now we want to store some data onto the data register. Remember, for command register, RS is equal to 0. For data register, RS is equal to 1. So that's why this is 1. And here, RW is equal to 0 because we want to write something. Just like your command register, there we had to take RS is equal to 0 and RW is equal to 0. Here, RS is equal to 1, RW is equal to 0. Because we are again writing some data, but not to the command register, rather data register. And then we're going to send or give corresponding 8-bit ASCII value for the character we want to show. And then after we have given all the signals, just like your clock pulse, just like your flip-flop, now this enable pin, we have to give high to low pulse or negative edge trigger signal to latch the data whatever we have sent, right? After that, we are going to see that corresponding character is being shown to the corresponding position of this display, right? So now if we understand this much, we can look at some assembly examples for 8051 where we will try to use this LCD display to show some characters. Okay, and you will see for most of the codes we go through these 3 basic steps. First of all, we initialize the LCD using some basic command codes. Then we will set the cursor position of where we want to actually start writing from, show the characters from, and then we send the characters, okay, in a form of 8-bit ASCII value. Okay, so before we begin, let us try to look at the connections we are going to give from LCD to microcontroller. So RS will be connected with pin 2.0, RW pin here will be connected with pin 2.1, and E pin, enable pin, will be connected with pin 2.2. okay, and these 8 pins here, D0 to D7, they will be connected with port 1. okay, so the whole thing will be connected with port 1 so that pin 1.0 will be connected with D0. In this way they will be connected, and pin 1.7 will be connected with D7 of LCD. In this way it will be connected. So now we can look at the code. So this is just one basic example of how we can show different characters onto the display. In this specific case, we will try to show no in the display. So let us start from here. So we are just defining here the pins we have connected with our microcontroller. So RS is connected with pin 2.0, RW is connected with pin 2.1, E is connected with pin 2.2, and we have used this EQU directive so that elsewhere in the code we can just use RS instead of pin 2.0, RW instead of pin 2.1 in this way. Okay, so just for our convenience. Now this is the whole code, but here we have 2 special subroutines to deal with the command writing and data writing. So this particular subroutine is for writing commands, and this one is for writing data to the display, to the LCD. So we'll first of all briefly look at that to understand how we can write data or command onto our display. Then we will look at the main code. So this one, you see, what we are assuming here is whenever we actually go into this subroutine, already we have the data we want to send to our display stored in register A, and that will be sent to our port 1. So that, you know, we looked at the connection that we have connected port 1 with the 8 pins of LCD, the data bus of LCD. So that means if I send the data to port 1 that will go on to our LCD data bus, right? And then what we are going to do, because here we are trying to write a command to LCD that will go to the command register, and for that RS should be 0, RW should be 0. We have already discussed about that previously, so that's why both of these bits are cleared. And then what we are going to do, we are going to send a high to low pulse to our enable pins, so negative edge trigger signal. So that's why first of all we are sending a high pulse to E, then giving some delay, and then making E 0, right? So that will give us a signal like that, from high to low, negative edge trigger signal. Now here why we are using this delay, because we have to have some amount of time before we move to the 0. Otherwise this negative edge trigger will not be properly registered by the LCD. Okay, so that's why we have given this delay, so that we have a proper high signal, then we have a proper low signal, so that this transition is properly recorded by the LCD. Okay, then let us look at writing data. So for this subroutine, we know again whatever data we want to send through the data bus of LCD, that we already have stored in A, that is what we are assuming, and then that will be sent to port 1, because port 1 is connected with our LCD. Then we are going to set our RS, because RS should be 1 for selecting data bus, because we are trying to write, so RW should be 0. And then we are going to send what, because again here we are trying to write some data, same kind of signal, negative edge trigger should be given here, that's why this is 1. We have enabled the pin with E is equal to 1, then some delay, and then we have cleared E. So again here we are getting a negative edge trigger, and that data will be sent. Okay, so if we understand this much, now we can look at the code. And also this is just one example of the delay we are using. We are not going to discuss how it works, we already know, but here from here we are going to start. So one by one, first of all, as we said, we are going to send some commands codes to our LCD display that will be stored onto the command register, basically just to control how LCD behaves. So these are some of these commands. So first of all, we are giving 38H to A. 38H is the command code for 2-line 5x8 font. Okay, to get that we have to give this command. We are just sending that to register A, because whenever we go to this subroutine, this data saved in A will be moved on to P1, that will go into the data bus of LCD, right? So that's why we have done that. So just after that we are calling this subroutine command, right, so that we can execute this portion. Okay, so after that this command will be stored onto the command register of LCD, and then we are going to give some delay, because in this particular code, this is just a basic code, we know after each of the execution we are doing, each of the command or data we are sending to our LCD may take some time to incorporate that. So that's why we check for busy flag, that is the most efficient way. But here we are not doing that, we are just assuming it will take some time, the LCD will take some time, and because of that, after each command we are sending, we will give some delay. Okay, then we are going to send the next command, which is OEH. So if you remember, OEH is command code for enabling display and cursor. Okay, but blink will be disabled, so just enabling display and cursor, for that this is the command. Then again we are writing the command, then delay, then this one is for clearing display. Because whenever we start the LCD, initially there can be some garbage value stored onto the data or command register, whatever. So that's why we are clearing the display, so no kind of data already is in the LCD. And this one 06H, so this is another initialization code. This basically is for making the display behave such that whenever we write something, the cursor will increment, not decrement. Okay, so it will move to the right after we write each character. Okay, if you remember from our previous discussion. So this is what this will do. So after giving all of this command, these are kind of like default. Initially we generally give those to properly initialize our display. Then now for this command, this one 84H, if you remember from our previous discussion, maybe here, yeah, so we have how 32 blocks, 16 in each line, and we can write characters anywhere, right? For each of the blocks we have different addresses, so starting from 80 to 80F, and for the lower line C0 to CF, right? So that's why we have selected here 84. 84 is basically 80, 81, 82, 83, 84, right? So this one, from this block we want to start writing, that's why we have selected 84. For the code here we have used 84. That means for line 1, position 4, we are going to start writing. That's why we have given that, and now we have called the command writing subroutine, and then we can give some delay. And now we are going to, here we are going to write anything we want. So you can just send the ASCII character like this. If you give this kind of notations here, this will be considered as an ASCII character of n as 8-bit value, and that will be sent to our register A. Okay, so 8-bit value will be sent to register A. Then we are going to execute the data write subroutine, and that will show the characters in this particular position. Okay, line 1 position 4, and that will increment the cursor position to position 5, and whenever we write the next character, this one O, it will be stored in line 1 position 5. So in this way the two characters will be written. So this is the basic procedures of how we can show different characters into our LCD display. So first of all we have to initialize the display using correct command codes. Then we can set the cursor position like this anywhere we want, and after that we write the data using their ASCII values. Okay. Okay, so let us look at the next example. In this example, we have just improved upon the previous code by checking the busy flag. In the previous example, we didn't have that kind of facility. We just waited for some time after sending each command or data. But a better way, a more efficient way, is to check the busy flag and then send the next data, right? So you will see that in this code, most of the things in the main code is similar like before, like the previous code, but here we don't have that delay after sending each command or data. So what is happening here, if we look at the command writing subroutine, you will see first of all we are calling a subroutine called ready, and here also in data writing subroutine, first of all we are calling a subroutine ready. So what it does, let us try to understand. So here this particular subroutine ready is checking for the busy flag and let us know whenever we are ready for sending next data. So before that, try to again remember that port 1 was connected with D7 to D0 of LCD, right? So that means we can say this pin 1.7 is connected with D7 of LCD. We know whenever we want to check the busy flag, that will come from D7 of LCD. So that's why we are trying to first of all set our pin 1.7 to make it an input pin, because we are going to take the data as input from LCD. That's why we have set it. Then we are going to give necessary commands to our LCD pins so that we can retrieve that busy flag data from LCD. So what is that? Because this data is coming from command register, so that's why we have to select rs is equal to 0. Then because we are trying to read that, we have to make rw is equal to 1. Okay, for writing rw is equal to 0, and for reading rw should be 1. And then what we are going to do, we are going to send a low to high pulse. Okay, so for reading, enable pin should get low to high pulse, from low to high. That's why initially we have cleared E, then taken some delay, then we have made enable pin 1, so positive edge trigger signal. If we do all this, we are going to get the data from pin 1.7, which is coming from D7 of LCD. So it will be either 1 or 0, and based on that we can make the judgment whether LCD is busy or not. So we know from our previous discussion, if D7 is equal to 1, let us look at there again. So this was the discussion. So after doing all of that, whenever we'll get the data from D7, if that value is equal to 1, we will know that LCD is busy, and if D7 is equal to 0, LCD is ready to receive new information. So let us look at the code again. Here you see we have given jump if bit pin 1.7. so that means if pin 1.7 is getting 1, we have to go to back, and whenever this pin is getting 0 value, we can just move on to the next line, which is going out of this subroutine, right? So what it is doing, whenever this value will be 1, we are not going out of the loop, so we will again do the same thing, checking and getting the data from D7. And if this pin 1.7 is equal to 1, that means LCD is busy, so we have to be in this loop as long as we see LCD is busy. And whenever this particular pin becomes 0 or getting the value 0 from D7, we can say LCD is not busy anymore. We can move on to sending more data to our LCD, right? So that is how it's done. Everything else is similar, so that's why we have this subroutine here every time called at the first line of command writing and data writing, because initially we are going to check whether the LCD is busy or not. If the display is ready, then we are going to send the command or the data. Okay, and everything else here is just like before, just like the previous code. Okay, so we will look at one other example, the third example, where we have made some more improvement to this code. So let us look at that, this one. So here we have taken help of indexed addressing. If you remember from your previous lectures, we can fetch data from code memory using movec and dptr. So similar thing is happening here. We have these two lines here. With mycom, we have these data, 8-bit data, which are basically, the command codes we used to send initially. So these are the command codes we generally send: 38 OEH, 01H, 06H, and this one is for getting your cursor to line 1, position 4. So all of them are given in this way so that we can fetch them one by one to send the specific command to our LCD. And then for this one, my data is basically the ASCII characters for the characters we want to write onto our display or show onto our display, right? So if you write it in this way, each of the characters are actually are represented using their ASCII representation, and each of the memory location will contain one of the characters. So we can fetch them one by one by getting their memory location, right? So all of the other things you can see here in this code, like this one, command writing, then this data writing, the delays we have here, all of them are just like before, just like the previous two examples we have seen. So from here we can say, so what we are doing, we are first of all we are going to send the command codes to our LCD to control the behavior. So that's why we have taken this mycom the address of the initial location, or the 38H wherever it is located, which is 300H. This particular location will be stored onto our DPTR. Then we are going to clear our register A, and this particular line here, A plus DPTR, is currently pointing to 300H location, and that data in 300H location, which is 38H, will be sent to our register A. Now we can write that command. Okay, so that 38H will be sent as command to our LCD. So in this way, you see all of the commands we have one by one will be sent to our LCD. And in this code, we haven't made that improvement of checking busy flag, but you can do that to omit this delay. You can do that, no problem. But after that, what we are doing, we are trying to look at our accumulator register A, because you see each time we are storing the data onto register A, right? And the last data in this particular sequence is 0. So whenever we reach here, that is the end of commands. So that will be identified by this particular line. So if accumulator is 0, then we can understand all of the commands are sent. We can come out of this subroutine and go to this particular line to send the data, right? So that's why we have that. And if not, what will happen, we can increment the DPTR each time and go to again C1. So you see, again we are going to C1. So that will basically get the next commands one by one, and whenever we reaches here, then it will be true, and because of that it will come out of this subroutine and go to send that subroutine, right? So here we are trying to send the data. So here we are going to load my data label, and that will give us the location of the first character here, H. Okay, so again, like before, we are clearing A, then getting the data from the first location of my data, moving that to A, and that will be actually sent to our LCD using data writing subroutine. And then we are going to give the delay for giving some time to LCD for internal operation. And here we are incrementing the DPTR just like before. So whether you give this command jump Z again before this line or not doesn't matter, because we can increment the DPTR, but that is not affecting the value of register A. So that means we are just checking whether register A is 0 or not, which is actually will point to this value. So whenever we reach here, we know all the data we want to send to our LCD has already been sent, so we can come out of this subroutine, right? So that will be checked here, and each time if that is not 0, we have to increment the DPTR to get the next character. That's why we have this increment DPTR instruction, and it will go to D1 again to do the same thing again, to write the next character, right? So in this way, whenever we reach 0, it will come out of the loop, and it will go to here, right? So this is basically an infinite loop. So whatever we have tried to do, write the characters onto the display, if that is done, we can just be here in this infinite loop and display whatever we want to display onto the LCD, right? So that's how we can improve the code for displaying different characters onto LCD. All of our discussions regarding LCD interfacing is complete, so we can move on to the next topic, which is keyboard interfacing. To understand keyboard interfacing with 8051, first of all, we have to understand how internally these things are built. So here we have one example of a 4x4 matrix keyboard. So here you can see we have 16 different push buttons connected with each other in a specific manner. So if we look at one push button here, you will see that we have two contacts here, and whenever you press the button, these two contacts are connected with each other, otherwise they are open, right? and also all of the push buttons are connected in such a way so that all the push buttons in same row are connected with each other in one of the ends, and also all of the push buttons that are in same column are connected with each other in another end. So in this way all of them are connected, but you have to understand the rows and column contacts that you can see here, this intersection, these are not connections. So rows and columns are not connected with each other. Be very careful about that. And you will see for each of the rows and columns, all the rows we have here, the 4 rows here, they are connected with supply voltage VCC 5 volt through a resistor of 4.7k. Same can be said for column as well. You see the 4 columns are connected with VCC through a resistor. Okay, so in one of the ends they are connected with supply voltage. The other ends will be connected with microcontroller. So these 4 rows and these 4 columns will be connected with microcontroller pins, and because of that we will understand somehow, or the microcontroller will understand somehow, which particular button has been pressed. Because you see, whenever we press a button, let's say for example this particular button, if that is pressed, this column and this row will be connected with each other. So based on that, microcontroller will understand that this particular button has been pressed. So we will look into the details of how that happens, and let us start that. Here you see, if we look at the connections we have given with the microcontrollers, port 1 and port 2 are actually used here, and 4 pins of port 1, basically we can say port 1.0, which is called D0 here, then port 1.1, port 1.2, port 1.3. so these 4 are actually connected with the rows of keypad. And for port 2, so port 2.3 here, and in this way this should be port 2.0. so these 4 pins of port 2 will be connected with the columns of the keypad, and port 1 will be used as output and port 2 will be used as input. So it will send some values to the rows, and based on that we are going to look at the values we are getting from the columns using port 2. Okay, so that is the idea. So what we will do, initially understand what happens. Like initially, if nothing else is affecting, the input ports here, port 2 should get what? Because the columns are connected with VCC through a resistor, and so it will basically work kind of like a pull-up resistor. So all of these pins will get logic high, logic 1, right? And what we are going to do, we are going to make all of these pins here of port 1 0. Okay, because this will be used as output port, all of the pins will be given logic 0, so that all the rows are getting 0 here. And if we check the input pin port 2 here, we are going to see generally whenever no key has been pressed, we are getting 5 volts, right? But if one of the key has been pressed, then that will make the row and column contact, right? So that means, let's say for example, if I say this 7 push button has been pressed, these 2 ends will make contact, and as a result this column and this row will be connected. So what that means, if D1 has been given logic 0, that will go through this path to here, So D3 will now get 0. Okay, so all the other ones will get 1 because these are not connected, right? This push button is not connected, this one is not connected, so they will directly get this 5 volt through the resistor. So this is how we are going to detect a key press. The general idea is that, okay, so initially we will just scan, and if we always get all ones, 1 1 1 1 to our port 2, that means no button has been pressed. And if we detect any kind of change from this value, then obviously we are going to understand that some key has been pressed. Okay, so that is what has been explained here. So you see, if we give 0 here, 0 here, 0 here, okay, so this is output port, so all of the rows are getting 0. And currently if no buttons has been pressed, so all of the values we'll get is 1 because they are directly connected with VCC through the resistor, right? And if a particular button has been pressed, for example, let's say for now, let's say this A has been pressed, that means these two ends will make contact. As a result, this row and this column are connected together. As a result, this 0 will go through this path to this path, right, to make this one 0, right? So we are trying to detect this change here. So if this kind of change happens, we can understand, obviously in this column some change has happened, right? Now what to detect is which row, because row and column will constitute to a particular key being pressed. Okay, so that's why what we are going to do is we are going to make one of the pins, one of the output pins 0 at a time and all others 1. Then check the input pins, what is the value. So for example, we will start with 0 1 1 1. If we make all the 4 pins like that of port 1, which is given as output, and then check the input pins, we are going to see that we are talking about the situation we talked earlier here. So we are assuming the key A has been pressed. That means, these two ends are making contact. And currently, if we have made the output pins like that, in the input pins we are going to get value like this without any change. All of them should be 1 because, if this is 0, there is no contact being made here. So as a result, all of the input pins D3 to D0 will get 1. Okay, then what we are going to do, we are going to change the sequence. So now we are going to make this one 0. Okay, in this sequence again we are going to check what happens. Here we are going to see similar thing, all of them are 1. So that means in this row no key has been pressed. Then we are going to change the sequence again. So we are going to make this one 1 1, D2 will be now 0. And now we are going to check again, and here you are going to see that, so here the value is 1011. So that means the key has been pressed in this row. So we know the column, we know the row. So in this way, row can be identified. Okay, so the detailed procedure is even more complicated than that. So we will look at that with the help of our assembly program. But before that, also we have to understand a practical problem we have to deal with whenever we use keypad. Okay, which is called switch bouncing or contact bounce. So whenever we press any kind of push button, because they are mechanical devices, what happens is they will vibrate within a very short span of time, maybe within the range of millisecond, but we will see this kind of vibrations. So contacts will go up and down within a very few milliseconds, but that will happen, and as a result that can cause problem, because you see in this region it is becoming 0 to 1 to 1 to 0. In this way it is changing. After that it stabilizes. So what can happen whenever we use these push buttons, instead of whenever you press the button, instead of a single key press, it can be registered as multiple press because of this situation. So somehow we have to deal with that and solve that problem. And the way we do that, this term is called debouncing. Okay, so there are two main ways. One of them is through the help of hardware, another one is through the help of software. So in our code, in our program, we will try to understand the software one. Hardware you can do, but mostly because this is easy to do, doesn't need any kind of hardware change, software debouncing is much easier and most of the time does the work very well. So because this is just voltage change, within a very short span of time, voltage is abruptly changing from high to low. Using any kind of RC network we can resolve that, smoothing that out. That is the basic idea. And for software debouncing, what we do, we just have to wait for some time until the signal becomes stable, right? So what we do, after we detect a button press, like in this initial condition, whenever we detect this button press, we will take some delay. We will wait for some time, that can be in general 10 to 20 millisecond. That is the amount of time generally push button takes for the stabilization. So we will again check what is the value. So if after that we again see that the button has been actually pressed, giving us the same value as before, that means button has been stabilized. So in this way we just deal with the bouncing effect. Okay, now we will look at this flowchart to understand the overall workflow of keyboard interfacing with 8051. Before we explain everything here, understand that whenever we press any key, any push button, we may take some time to release that key. Okay, it may take like 1 second or 2 seconds, something like that. But for microcontroller to figure out that key press and to execute whatever needed for that key press may take a very little amount of time, maybe 50 milliseconds or 100 milliseconds, something like that. So after it completes that, obviously it cannot just again do the same thing, because the key is still pressed, right? So what it does, it will again go to its initial condition to look for another new key press. But before that, it has to first of all figure out that the previous key that has been pressed now has been released. Understand, right? So that's why in this flowchart, the first portion is for that, to figure out whether the key that has been previously pressed is now released. Okay, so we will start here, and like we had discussed earlier, we are going to ground all the rows and then look at the columns. What are the values? If all of the values are 1, that means basically no key has been pressed, right? If the value here is anything other than 1111, that means obviously some key has been pressed, right? That is the general idea. So similar kind of thing here, we are grounding all the rows, then reading all the columns. And as we said, first of all, we will try to figure out whether the key that has been previously pressed is released or not. We are going to deal with that. That's why here we are trying to figure out whether the key that has been pressed before is released or not. If no, we have to again read the columns and wait for that key to be released. And if that is released, we can say yes here, and again we are going to read the columns. Now we are into the main code. Now we are going to check for new key press. Okay, so we are going to read the columns and we have to find out if any key has been pressed or not. So that means we are just looking at these values. If all of them are 1, that means no key has been pressed. So if any value other than 1111 is there in the input pins of port 2, we are going to understand that a key has been pressed and we can move on to the next stage. Okay, so here, if a key press has been detected, we can wait for some time for that debouncing, right? So that will be generally like 10 to 20 millisecond. After waiting for that amount of time, we are again going to read all the columns, and if we get the same value like before, so obviously that means a key has been pressed and we can move on to the next stage, right? And if not, that means either that can be an erroneous signal coming from the buttons, so that means we have to again go to the previous stage, again read all the columns for detecting a next key press, right? That will also deal with the issue of debouncing as we discussed before. So if we are getting the same signal, obviously we can move on to the next stage here. So what we're going to do, as we said before, now we know a key has been definitely pressed, but we have to figure out in which row that key belongs, in which column, as well as in which row that particular key belongs to. We can then identify the particular key, right? So we are going to ground a specific row, so something like that. First of all, 0 1 1 1, then check all the columns whether they are all ones or not. Then we are going to make something like this, 1 0 1 1, right? Then check all the columns. In this way we will do that for 4 times. Okay, so whenever we find that the values we get here in this port 2 are not all ones, we can understand at that particular row key has been pressed, and accordingly we can also find out the column, right? So in this way this will be done. Okay, now let us look at the assembly program for interfacing keypad with 8051. So here in this whole code, first of all, let us look at this portion. Here we have stored the corresponding ASCII character for representing specific buttons. So if we remember, in our keypad we have 16 different buttons and each of them represent a hex character. Okay, so 0 up to F, and for representing each of them we have stored these values here, these characters here, and they are arranged in such a way so that if we know the row and the column of the key which has been pressed, using that we can locate corresponding ASCII character that represents that button, right? So how is that? Like you can see, we have arranged the values in 4 different rows, right? So row 0, row 1, row 2, row 3. In row 0 we have these 4 values, just like you have in the buttons. In row 0 we have 0 1 2 3, and they're also arranged in such a way based on the column we can find them out. So column 1, column 2, column 3, and column 4. So if key 3 has been pressed, that means that should be what? Row 0 and column 3, just like the way they are distributed here, right? So to explain the example, maybe we can assume that for a certain case this button A has been pressed, and based on that how the code will respond and how that will be executed to find the corresponding ASCII character that represent this button, we will try to understand first. Okay, so let us start with here. So here P2 has been given FFH so that we can configure P2 as an input port. If you remember, from here port 2 will be used to read the column, so it will be used as input port, and as a result we are giving FF all ones to its pin to configure it as input port. Okay, and port 1 is connected with the rows, so we will output different values here to give different values to these rows and then read the columns. That is the idea. So we give values to rows and read the columns. And again I am going to repeat that in port 1 the least significant 4 bits are actually connected with the rows, like pin 1.0, 1.1, 1.2, 1.3. These are the pins, and here also the least significant 4 bits. So pin 2.1, 2.2, 2.3 and 2.4 are the pins connected with the columns. Okay, so if we understand that much, we can look at this line. So here, first of all, we are trying to give all zeros to port 1. Okay, and then we are going to read port 2 and save the value onto A. So what is that doing? We are just basically giving zeros to the rows. Okay, it's like that, 0 0 0 0 given to port 1, and then we are going to read port 2 and save the value onto A, right? So that is what we are doing, and then we will use this command ANL, logical AND. So let us try to understand what it does. Let's say if I have commands like this, ANL, A comma, then we have value like this. Okay, so what it will do is, let's say for example currently maybe we have some value like this inside of register A, so 1011 1100 for example, just, and this is the value we have as another operand, right? So if we do that after execution of this command, what will happen to register A is we are just going to do bitwise AND. So all of the bits will be bitwise ANDed together. That means for these 4 bits, whatever value we have will go through here, because 1 1 should be equal to 1, and if either of the bits are 0, then that for that bit the result should be 0. That's the idea. So these values, this, because all of the bits here are 0, whatever comes here, that will just become 0. But here, whatever value we have, because that will just pass through, we are going to get that value. So we are kind of like masking here. So because only the least significant 4 bits are connected for both of the ports, this port and this port, that means the most significant 4 bits are not needed. That's why we can just omit those. To do that, we are using this command. Okay, so whatever we get in register A, we can omit the values for most significant 4 bits. We only need these 4 because these 4 are connected with the keypad rows and columns, right? So that's why we have used this command, and we are going to use this command throughout our example here, because in most of the cases we don't need those 4 bits, most significant 4 bits. That will just cause problem to our calculation. So that's why. And then this line, to understand that, first of all we have to again recall the thing we discussed in the last page is whenever we press any key, it takes some time to release that, right? But before that, if we have already executed the code for that, like for example, if it takes at least 1 or 2 seconds to release the key for me, but the code takes only 100 milliseconds to execute that code. So after executing the code, which actually represents that key press, after completing that, obviously it has to return to initial position, right? So it cannot just again do the same thing, because it has to wait for that key to be released to again look for new key to be pressed. That's why, so we have this portion for that here. So what we are going to do, we are thinking of a situation like whenever we have already executed everything for a key press, we will come here and basically it will say again return to here, right? And that means if I come here, I have to wait for that key which I have pressed to be released first. After it has been released, now we can look for another key to be pressed. That's the idea. So that's why first of all what we will look at is we will here first of all make all the rows 0 and then look at the columns. If any of them is not 1, let's say for example if I get some value like that, that means a key is still pressed, not released, so still we have to wait for that key to be released, and then we can move on to our identification of next key press, right? So that's why in this particular K1 subroutine, what we will look at is whether all the columns are 1 or not. That is how we are doing. So we are comparing our result in register A with this value. If they are equal, that means if a key had been pressed earlier, that has been released now, and we can move on to next line basically. But if they are not equal, we have to go to K1. If these two values are not equal, that means what? The value is anything other than 1 1 1 1 for the columns, right? So it is anything other than 1 1 1 1, which is, it can be something like this, or it can be anything else, but basically that will detect a key still being pressed. That's the idea. So if that happens, we have to wait for that key to be released to move on to next section, right? So if that key has been released, let's say from the previous case, then we can move on to this line here, K2, and initially here we have one delay. To discuss about that, we have to first of all discuss these 3-4 lines, then we will understand what is the purpose of this delay here, right? So try to understand what we are doing. Again, here we are trying to read from the columns. So port 2, we are reading something from port 2 and moving that to A. So reading from port 2, and then we are going to move that to register A. Then we are going to do the same masking we had done before to get just the least significant 4 bits, then compare that with all 4 ones. Okay, so we are trying to again compare whether they're all ones or not. So all ones or not. So now here what we are trying to do, now here we are trying to detect whether there is any key press or not. Previously in this subroutine, we try to check whether previously pressed key that has been released or not, but here we already know that key has been released, so we can check for a new key press, and that will be done through this line. So what will happen if both of them are equal? That means any key has not been pressed. So that means we can just go to this line here, that will just move us back to this K2 because they are equal. If they are not equal, we will satisfy this comparison, this condition, then we can move on to this label called over, right? So if any key is not pressed, we are going to go to this line, and if any key has been pressed, we will go to this line. That is the idea. And let us discuss for the case where a key has not been pressed. So if that doesn't happen, we are going to go to K2 and it has this delay. So now the purpose of this delay is, after each time we are checking, and if there is no key press, we will wait for some time, some delay, and then we will again check. So maybe every 20 millisecond or 30 millisecond we will have this delay. So every 20 millisecond we are going to check for key press. That's why we have this delay, basically to add some buffer. Other than that, we have to execute much more times to check for that delay, and we have to fetch data from port 2 from the columns, right? So that's why we have this delay. So let's say if a key has been pressed and we actually see that happening and come to this particular line over here, also we have another delay. This delay is basically for doing the debouncing. So as we said, whenever we want to debounce, we check for a key to be pressed. If the key has been pressed, we wait for some time, maybe 20 milliseconds or such, and then again check whether that key is actually being pressed or not. If for both of the cases key has been pressed, we can certainly or confidently say that the key has been pressed without any issue and move on to detecting the particular key that has been pressed. So that's the idea here. So that's why we are again going to check similarly but after some delay. So here what we are doing, we are again taking data from port 2, so reading the columns and moving that to A, again masking the least significant 4 bits and again comparing that with 1111. So after comparing all of that, if they are equal, that means what? Maybe previously whatever we have gotten, that key press, that can be erroneous, and we can move on to the next line K2, and that will return us back to here again for checking the key press. But if let's say if we see that these two values are not equal, that means again we have detected some key press just like before here. So that means we have to go to this line over, and here we are confident that a key actually has been pressed, and we can move on to the procedure of detecting a particular key being pressed, that is by detecting the row and column of that particular key position, right? So how that is done, let us try to understand. So if you remember from previous slide, we said that whenever we actually detect that, confidently detect that a key has been pressed here, what we do, we try to find out row and column of that particular location. So what we do, we actually give here, like initially what we did, we gave all zeros, then detected some change in this output pins, right? So anything other than 111, if that happens, obviously a key has been pressed. But after we have confidently detected that key has been pressed, now what we are going to do, we will try to find out in which row that key is located. So that's why we are going to give something like that. So initially, let's say we will give 0 1 1 1, and then we will check what is the value here. If all of them are 1, that means in this row no key has been pressed. Then we will change that to 1 0 1 1. Then we will check here again. So if again here we see all of them are 1, that means in this row as well no key has been pressed. So in this way we said that for our case, for explanation of the code, we are assuming that key A has been pressed. Okay, so let's see in the code how that happens. So you see, first of all we will move this value onto port 1. Just look at this 4 values, that will be important because we are not caring about this portion. This is most significant 4 bits which are not required. So in this case, just like here, 0 1 1 1, so you can see the same thing, 0 1 1 1. This is the value we are moving to port 1, and then we are going to look at the columns by checking at port 2, and this value is sent to A. We are going to mask only the list for significant 4 bits because this is the one we need. Then we are going to compare with all ones. So if we compare that with all ones, and if both of them are equal, that means no key has been placed in row 0, we can move on to the next line. But if they are not equal, obviously there is some mismatch between these two values. Maybe in any of the columns the value is not 1, that can be 0. So in that row, obviously some key has been pressed, right? So if that happens, we can just move on to row 0, this subroutine. Otherwise we will just move on to the next line like that. So here what we have, like from here up to here, this is for row 0. Then from here up to here we have for row 1. From here up to here we have for row 2, in this way, right? For checking whether that key press belongs to that particular row or not. That's the idea, right? So in all of the cases, what we are doing, we are just comparing. If they are equal, we are going to jump to that particular subroutine because we have identified the row. Now we have to identify the column. That's the idea. So for our case, we said that A has been pressed. So if A has been pressed, we can say the value we had sent in that case was 1 1 0 1, right? This is the value we have sent, and for that case we are going to see that the value we will be getting at the port 2 will be something like this, right? So 1 0 1 1, right? So if that is the case, you see the value we have sent for row 2 is this one, right? 1011, just like here, you see 1011. This is least significant bit, this is most significant bit. So here also this is the 4 bits, and after doing that we are going to say that these two values will not be equal and we have to move to row 2 here, right? Afterwards, what we are going to do, we are going to execute this line, which is we are going to get the address from k code 2, because 4 possible ASCII values for 4 possible key are stored in k code 2. That's why we will store the location of first character 08 onto dptr. So that's why k code 2. Now we have to find out what is the column. Based on that, we will have to increment the value of dptr so that we either get the value from index 0 or index 1, index 2 or index 3 based on the column, right? So that will be done using this short jump find. So if we go there, try to understand for all of the cases, row 0, row 1, row 2, row 3, the inside of those we have similar code. Only difference is what memory address we are actually storing onto dptr. So based on the row which has been identified, we just have to give a different initial address, right? So that is done here. For row 0, that should be k code 0. For row 1, that should be k code 1, in this way. And in which row the key has been pressed, that is identified by this particular codes, right? So now let us look at this find, which will help us to identify the column of the pressed key. So here in this find, you will see first of all we have this command called rrc, which is rotate right with carry. Okay, so what is rotate right with carry? To understand that, let us look at this particular example. So rotate right with carry means, let's say if this is register A, this is the most significant bit, this is the least significant bit. Whenever you execute this kind of line rrca, the value, all the bits will shift to the right by 1 bit, including carry. Okay, so just for understanding, let us look at this example. First of all, we are clearing the carry to make carry is equal to 0. Then we are moving 26h onto A. So that value is what? 10010, this is 2, and 0110, so this is 6. This is the current value stored inside of register A. So in this currently stored value of A, if we execute rrc once, what will happen? Every bit will shift towards right by 1 bit. So that's why you see this 1 is here, but this 0 value will go to carry. Just like from LSB to CY, this 0 will come to carry, and initially whatever was stored in carry, which is 0, will come to the most significant bit of our register A. That is what is happening, right? Then again in this current value of register A, if we again execute rrc, we are going to see that everything again shifting towards right by 1 bit. So you see this 1 will come here, this 1 will come here, something like that, you see, and the one we had here, this will go in carry, and carry previously had 0, that will come here in this way. So everything will shift including the carry. And then again if we execute the same command, again you see this one has come here and this one has come here, right? And this one, this carry previously, now it has gone here. So in this way it will just rotate right. So how it will help in our case? To understand that, you have to understand, like for row 2, whenever we had previously identified in this line, right, A was compared with this one, but what was the value we got in A? This is the value we had given through the rows, and afterwards this is the value we got, right? through the columns. So A should currently have the value saved something like this: 0 0 0 0 0 1 1 1, right? This is the value currently saved in A, and now somehow we have to find which bit is 0, because that will correspond to the particular column. In this way, in this case, that column is the third column, or column 2. Indexing, in terms of indexing, it starts from 0, so we have to say column 0, column 1 and column 2, right? So that's why we have to somehow find that in this location we have 0 which corresponds to column 2. So how to do that? We will take help of this rotate right with carry. A has value of what? 0 0 0 0 1 0 1 1. Now after you execute this line RRC here, what will happen? We will get 1 into our carry, right? The first RRC will give us the least significant bit here, 1, and after that we are going to look at the carry whether that is 0 or not. So if that is carry, we are going to satisfy this condition and we will say that is matched, right? Otherwise we have to increment the DPTR. Okay, so that means if there is 1 here that is not equal to 0, we have to move on to this line. Now DPTR will be incremented by 1, right? Plus 1. Then we are going to again go to the initial line of find. Again we are going to execute RRC. That will give us the next value into carry, because every time you do that, register A will shift towards right by 1 bit, giving the least significant bit to carry. So in the previous case that was this value, now this is this value. So again also this is not, the carry is not equal to 0, so we have to again go to here. DPTR will be incremented by 1 again, and then we are going to again go to find here. And afterwards when we again execute RRC, we are going to see that this particular value will come to carry, and that value is equal to 0. So this condition will be satisfied. We have to go to this line match here. The idea is, whenever initially we had reached this line, we had inside of our DPTR the location of ASCII character 8, right, which corresponds to first column, right, column 0. What we have to do, somehow we have to increment that memory location or that address to represent A. So that's why 1 plus 1, this 2 has been added. So right now in DPTR we have the memory location or the address of ASCII character A, because this is the character which was pressed. So how we have done that? By looking at this 0 value with the help of rotate right with carry, RRC, right? So in this way, after we have reached here match, we are going to clear register A for the sake of using A plus DPTR, and DPTR currently has the corresponding value of correct row and correct column for the key which has been pressed. That will give us the value of ASCII character A. We will move that to port 0 to show that basically, let's say. And finally, after doing all that, we can move on to K1 again at the initial position, right, to again look for another key to be pressed. But here again I will explain that whenever all the execution has happened and we have reached K1, that means we have to check whether the key that is already pressed right now, whether that has been released or not. So if that has been released, then we can move on to K2 and start checking or scanning for next key press, right? That is the idea. So this is how it works. I know this seems very complicated the way this code has been written, but hope you understood. That's all for this lecture. And also I want to mention that in your experiment 4, keypad interfacing, the lab sheet contains the whole code. I'm not going to explain everything from there, because in that code you will see that that code is just combination of this code and LCD interfacing. So what we have done there is we have connected both LCD and keypad, and we want to press something in the keypad, that value will be shown in the LCD. That is the idea. So I hope you will understand by just by looking at that code, because nothing is new there in that code. Everything is just like what we have discussed in this lecture, both in terms of LCD interfacing and keypad interfacing. Yeah, that's all for this lecture, I guess.